Welcome back to my series of videos on mathematics for economists. In this video, I'm going to go through two examples for optimization subject to inequality constraints. So I'm going to specify the Kuhn-Tucker conditions, identify a set of candidate points that satisfy the Kuhn-Tucker conditions, then evaluate the objective function on the set of points in order to decide which one actually yields the highest value of the objective function. Then I'm going to check sufficiency, and I'm going to check constraint qualification. So let's start with this example here, where we have a maximization problem for a linear objective function 3x plus 4y, such that two constraints be satisfied. One is that the vector of choice variables x and y have length less than or equal to 2, which means that x squared plus y squared is less than or equal to 4. And the second constraint is that minus x be less than or equal to minus 1, which is the standard form for x larger than or equal to 1. So we begin with specifying the Lagrange auxiliary function. So this is L of x and y given by the objective function 3x plus 4y minus first Lagrange multiplier times the left-hand side of the constraint minus the right-hand side of the constraint. And likewise for the second constraint. The way we have specified the Lagrange auxiliary function now is that the Lagrange multipliers must be positive numbers. If we arrive at a negative Lagrange multiplier, it does not satisfy the Kuhn-Tucker conditions, and we have a contradiction, so to say. Okay, then we can list the four resulting Kuhn-Tucker conditions, and I'm just going to number them in this fashion so that I can refer to them as we go along. The first two involve the partial derivatives of the Lagrange auxiliary function with regard to the choice variables x and y, and simply set the first derivative, the first derivatives equal to 0. So the one with regard to x is 3 minus 2 lambda 1 x plus lambda 2 be equal to 0, and the second is the partial derivative of L with respect to y, which is 4 minus 2 lambda 1y be equal to 0. These are identical to the conditions you would write down under equality constraints. And then we get to the complementary slack conditions, which are different from the case of equality constraints. So complementary slack says that the Lagrange multiplier times the slack in the constraint, which for the first one is x squared plus y squared minus 4. The product with the Lagrange multiplier must be equal to 0. This means that if there is slack in the constraint, that is to say x squared plus y squared is strictly less than 4. If there is slack in the constraint, then x squared plus y squared minus 4 is strictly less than 0. In this case, economically, you're not exhausting your resources, which means that imposing this constraint does not cost you anything, so you're not incurring opportunity costs, so your shadow price is equal to 0. So that the product of these two numbers, 0 with something strictly negative, is equal to 0. Or the other way around, if the constraint is not slack, but is active or binding, so that the slack is equal to 0, then the Lagrange multiplier is going to be strictly positive, because you're essentially operating at capacity, and imposing the constraint is actually costing you in terms of opportunity costs. If you were to increase your capacity, so to say, from 4 to 5 to 6 units, you would for every unit gain lambda 1 units in your objective function. Yeah? So this is complementary slack, and we get the corresponding expression for the second constraint, of course, complementary slack. So we have, just as in the case of optimization under equality constraints, we have 4 equations and 4 unknowns. But these equations are nonlinear, so we cannot solve this by methods of linear algebra. And we can also not say much about the existence of solutions or how many there are. We just kind of have to work our way through. Working our way through means that in some sense we keep substituting until we arrive at hopefully one equation and one unknown that can be solved in an analytically tractable fashion, and then we can work our way backwards by plugging in the values that we get and hopefully solve the system of equations this way. Sometimes one is lucky enough that one can say from looking at these equations something about some of the involved variables, irregardless of the configuration of activity and inactivity of the constraints. But it is certainly a safe way to just go through all the combinations there are. So here in this case, where we have 2 constraints, we can look at 4 different cases. Both constraints are active, both constraints are inactive, constraint 1 is active, constraint 2 is inactive, or constraint 1 is inactive and constraint 2 is active. So with 2 constraints, this is a still doable task. Of course, if there are more than 2 constraints, this can become a bit confusing quite quickly, and then we are hopefully in a situation where we can solve for some of the variables without having to go through all these cases. But here we can certainly do it, and we can be certain that we're not going to miss anything if we go through all possible cases. So let's do this, and let's begin with a case where both constraints are binding. Both constraints are active. What does this mean? This means that x squared plus y squared is equal to 4, and this means that lambda 1 is strictly positive. And it also means that x is equal to 1, the constraint is binding, the second one, and therefore the second Lagrange multiplier is also positive. Now, if x is equal to 1, then x squared, still 1, plus y squared is equal to 4 from the first constraint, and we get that y squared is equal to 3, and therefore y is equal to the positive or the negative square root of 3. So we have 2 possible cases to consider. Let's begin with the case where y is equal to the positive square root of 3. Then I look at condition number 2, which is 4 minus 2 lambda 1 y equal to 0. And now I have y equal to square root of 3, so I get 4 minus 2 times square root of 3 lambda 1 equal to 0, and from that I get a value for lambda 1, namely 2 over square root of 3, which is a positive number, so that's certainly good. With this, I go into the first condition, which reads 3 minus 2 lambda 1x plus lambda 2 is equal to 0. Now I have x equal to 1, and I have lambda 1 equal to 2 over square root of 3, so I have 3 minus 4 over square root of 3 plus lambda 2 is equal to 0, and from that I get that lambda 2 is equal to 4 over square root of 3 minus 3, which unfortunately is a negative number, so this is not satisfying the Kuhn-Tucker conditions, and I am not getting a candidate point from this case. Then I move on to the second subcase where y is equal to the negative square root of 3. And I can see now that if I proceed the same way from the second condition, 4 minus 2 lambda 1 y, now y is minus square root of 3, so this is plus 2 times square root of 3 lambda 1 equal to 0, I get right away that lambda 1 now is a negative number, so this is also not getting me anywhere. So no candidate points here. We move on to the second possible configuration, where constraint 1 is binding, active, and constraint 2 is slack, not binding, inactive. This means that x squared plus y squared is equal to 4, lambda 1 therefore strictly positive, x is larger than 1, so constraint number 2 is slack, and lambda 2 is therefore equal to 0. Yeah. Now I can certainly write from the first constraint, I can write x as plus or minus the square root of 4 minus y squared. And since x is supposed to be larger than 1, I can also eliminate the negative case here. So I only need to consider the positive case. So with this I go into the first condition, 3 minus 2 lambda 1 x equal to 0, because lambda 2 is equal to 0. I can thus write x is equal to 3 over 2 lambda 1. I'm going to use this later. I can also write, because I have x is equal to the positive square root of 4 minus y squared, I can also write 3 minus 2 times the square root of 4 minus y squared times lambda 1 is equal to 0. And this gives me an expression for lambda 1 in terms of y, namely 3 over 2 times square root of 4 minus y squared. Now I go into the second condition, which reads 4 minus 2 lambda 1 y is equal to 0. Now I plug in lambda 1, so I get 4 minus 3y over square root of 4 minus y squared is equal to 0. I multiply the equation through by the square root of 4 minus y squared. So I get 4 times square root of 4 minus y squared. And then I have minus 3y equal to 0, so I bring this over to the right-hand side, so I have positive 3y here. Now I square the whole affair. 16 times 4 minus y squared is equal to 9y squared. Or 64 minus 16y squared is 9y squared. Or 64 is 25y squared. Or y is equal to plus or minus 8 over 5. So this is the first time that I am arriving at one equation and one unknown, and I can actually solve it. So I have my first numerical value for one of my unknowns. Well, actually, we have already assumed that lambda 2 is equal to 0. So by definition of the configuration I'm looking at here, I have lambda 2 already, but this is the first one that I could calculate by repeated substitution of in my system of equations here. Yeah, so I get two candidate values for y. Now I'm going into my expression for lambda 1 that I had derived here, 3 over 2 times square root of 4 minus y squared. And since this is y squared that is entering, I don't need to worry about the plus or minus 8 over 5. So I get that lambda 1 is equal to 3 over 2 times the square root of 4 minus now 8 over 5 squared. This is 64 over 25. That's the square root. And this is, okay, so now what is the radicand? That's 4 times 25 is 100. So I have 100 over 25 minus 64 over 25. That is 36 over 25. And the square root of 36 over 25 is 6 over 5. So I get 3 over 2 times 6 over 5. And this is equal to 5/4 if we think about it. This is a positive number, so that's good. Now I can go and calculate x from this expression that I arrived at upstairs here. So x is 3 over 2 lambda 1. So this is 3/2 times 4 over 5 or 6 over 5. Yeah, so I have, through repeated substitution, arrived at one equation and one unknown, solved, and then I went back and plugged in with these solved values and could work my way backwards, and now I have all 4 values. I have x equal to 6 over 5. I have y equal to 8 over 5 and minus 8 over 5. And I have lambda 1 equal to 5 over 4, and I have lambda 2 equal to 0. So I get 2 candidate points from this. These are x and y equal to 6 over 5 and 8 over 5, and x and y equal to 6 over 5 and minus 8 over 5. Good. 2 cases are covered. 2 to go. Case number 3. Constraint 1 is inactive, is slack. Constraint 2 is active, binding. This means that x squared plus y squared is strictly less than 4, which means that lambda 1 equal to 0. And this means that x is equal to 1, which means that lambda 2 is strictly positive. Go into constraint 2, which says 4, into condition 2, which says that 4 minus 2 lambda 1 y is equal to 0. Now lambda 1 is equal to 0, which means 4 is equal to 0. If this is not a contradiction, then I don't know what is. So no candidate point from this case. 4. Both constraints are inactive. This means that x squared plus y squared is strictly less than 4, lambda 1 therefore 0. X is strictly bigger than 1, lambda 2 therefore 0. I can go into condition 2. Since lambda 1 is equal to 0, this is going to give me the same contradiction as the other case, as the case before. And so I also get no candidate points from this case. So I'm left with the 2 candidate points that I've found. So now I can go ahead and check the maximality of the candidate points by evaluating the objective function on these points. So I'm interested in the function value of the objective function for x equal to 6 over 5 and y equal to 8 over 5, which is 3 times 6 over 5, 3x, plus 4y. And this is equal to 18 over 5 plus 32 over 5. So this is equal to 10. And then I can already anticipate I'm not going to get anything from the negative value for y, because all I'm going to do is here, I'm going to subtract this term, and that's certainly not going to maximize the function. So I get 8 minus 32 over 5 here. So this is minus 14 over 5, certainly smaller than 10. So this is my candidate for a maximum. So let's check sufficiency. And here we answer the question, is the Lagrange auxiliary function concave if we understand it as a function of x and y in the optimum candidate? And this means, since we're going to understand the Lagrange function as a function of x and y, we're not going to plug in x equal to 6 over 5 and y equal to 8 over 5. It's going to be a consideration of the function in x and y. But we're going to plug in the values for the Lagrange multipliers that we found in this point, and this is lambda 1 equal to 5 over 4 and lambda 2 equal to 0, because constraint 2 was slack. So we get that the Lagrange auxiliary function for these specific values of lambda 1 and lambda 2 is equal to 3x plus 4y, now minus lambda 1, so minus 5 over 4, times the right-hand side, the left-hand side of the constraint minus the right-hand side of the constraint. So in parentheses, x squared plus y squared minus 4. And if we multiply this out, we get minus 5 over 4x squared minus 5 over 4 y squared plus 5. Yeah, so these are negative parabolas in x squared and y squared, and we're adding a linear term 3x and 4y. This still renders the function concave in x and y, and this means that we are indeed looking at a maximum. So x, y equals 6 over 5 and 8 over 5 is a maximum. The last thing that remains to be checked is constraint qualification. Constraint qualification. Well, we can quickly check that constraint qualification holds in the maximal point. So the objects to consider are the gradients of the constraint functions. So since the constraint function g1 is given by x squared plus y squared, the gradient is 2x, partial derivative of x squared plus y squared with respect to x, and partial derivative of x squared plus y squared with respect to y. And the gradient of the second, which is minus x less than minus 1, with respect to x, minus x, derivative with respect to x, that's minus 1. And y doesn't figure, so it has a coefficient of 0. So irregardless of the value of x and y, the gradient of the second constraint is minus 1 and 0. So the gradient of the first constraint in 6 over 5 and 8 over 5 is 12 over 5 and 16 over 5, and the gradient of the second constraint in 6 over 5 and 8 over 5 is minus 1 and 0. these two vectors are linearly independent, and so constraint qualification holds in the optimum. But the interesting question now is, are there points floating out there where constraint qualification does not hold, and we did not pick them up in the Kuhn-Tucker conditions, therefore, but the objective function actually assumes a maximum on those points. Yeah, this is the interesting question when one checks constraint qualification. Have we missed points by focusing on the Kuhn-Tucker conditions because constraint qualification breaks down in those points and Kuhn-Tucker is not able to pick them up? So this would be points where, so where could it go wrong? Check for points where the gradients of the constraint functions are linearly dependent. Yeah. What would those points be? Where are the vectors 2x, 2y, and -1 and 0 linearly dependent? Well, this would be for y equal to 0 and for well, x anything, because 2x then is something, not anything, but something not equal to 0. So x any non-zero value, because then this is certainly a multiple of -1 for a properly chosen coefficient. However, we also have to satisfy the second constraint that x be bigger than 1. So it can actually not be just any x, but any x bigger than 1, so that it satisfies the second constraint. Yeah. Well, with that we can go into our. Let's start from the first constraint: x squared plus y squared be less than 4. Now y is equal to 0. This means that x squared is less than or equal to 4, which means that x is less than or equal the positive or the negative square root of 4, which is 2. Now x be larger than 1, which means we can forget about the negative case. So we see that we have to look at check points where y is 0 and x is in the left open interval 1 and 2, yeah, because x must be bigger than 1, but less than or equal to 2. So, but we are only interested in maxima we may have missed. So if the objective function is given by 3x plus 4y, then and y is equal to 0, then we have just the objective function 3 times x. So we want to pick then certainly the biggest value for x. So we only need to look at the point 2 and 0. This is the interesting point to check. And here f of 2 and 0 is equal to 3 times 2 is 6. This is less than the value of 10 that we have already found. And so we did not find a point here that actually yielded a higher value than the one we have already identified. And from this we can then finally conclude that the pair 6/5 and 8/5 is indeed the maximum, such that the constraints hold. Yeah. End of example number 1. let's do the same thing for a second example with maybe slightly more interesting objective function. So let's say we have the problem we want to maximize with respect again to two choice variables x and y, the function given by 2x squared plus 3xy, and the constraints be g1 is 1/2 x squared plus 4 is less than or equal to 4, and the second constraint be minus y less than or equal to minus 2, or y larger than or equal to 2. Then, just as before, we set up the Lagrange auxiliary function, objective function, minus Lagrange multiplier, left-hand side of the first constraint, minus right-hand side of the first constraint, minus second Lagrange multiplier, left-hand side, minus right-hand side of the second constraint. And again, lambda 1 and 2 must here be positive. Then we can collect the Kuhn-Tucker conditions. First two again involve partial derivatives with respect to the choice variables with respect to x, 4x plus 3y minus lambda 1x b0. Second partial derivative of L with respect to y, 3x minus lambda 1 plus lambda 2 be equal to 0. So far as inequality constraints, now complementary slack, lambda 1 times the slack, it's essentially standing right there, 1/2 x squared plus y minus 4 be 0, and finally lambda 2 times minus y plus 2 be 0. And again, we have 4 equations and 4 unknowns, x, y, lambda 1, and lambda 2. And again, we're going through the different configurations of activity and inactivity of the constraints. And so we begin again with the case that both constraints are binding. Both constraints are binding. This means that 1/2 x squared plus y is equal to 4, and lambda 1 therefore strictly positive, and y is equal to 2, and lambda 2 therefore strictly positive. Then the first constraint says 1/2 x squared plus y, which is now 2, equals 4, or in other words, 1/2 x squared is 2, or x squared is 4, or x is plus or minus 2. I have 2 subcases to consider, therefore. Let's start with the positive one. I'm looking at constraint number 1, which reads, condition number 1, from the Tucker conditions. Condition number 1 reads 4x plus 3y minus lambda 1x equals 0. So 4x is 8, 3y is 6, x is now plus 2, lambda 1 equal to 0. I get that lambda 1 is equal to 7, which is a positive number, so that's good news. I go into condition number 2, which reads 3x minus lambda 1 plus lambda 2 is equal to 0. So I have 6 minus 7, as I found now, plus lambda 2 is equal to 0. This means that lambda 2 is equal to 1, which is also a positive number. Again, good news. And I have found a candidate point. The candidate point is x and y is equal to 2, and 2. And the corresponding Lagrange multipliers are 7 and 1. Let's look at subcase B, where x takes the negative value of the square root, so minus 2. I go into condition 1, again 4x plus 3y minus lambda 1x is equal to 0, and now I plug in x equal to minus 2, so I get minus 8. Y is still 2 because the constraint is binding, so this is still plus 6. And now minus 2 is plus 2, lambda 1 equals 0. I get that lambda 1 is equal to 1, which is a positive number. Good news. I go into condition 2, 3x minus lambda 1 plus lambda 2 is equal to 0. So this is minus 6. Lambda 1 I found is 1 plus lambda 2, b0, meaning lambda 2 is 7. The two have switched roles. This is a positive value. Also good news, I have found another candidate point. This is x and y are equal to minus 2 and 2. So here the first case where both constraints are binding gave me 2 candidate points. I go into the second case. Constraint 1 is active. Constraint 2 is inactive. Activity of the first constraint means 1/2 x squared plus y is equal to 4, and the corresponding Lagrange multiplier is strictly positive. Inactivity of constraint 2 means y is strictly larger than 2, and the corresponding Lagrange multiplier is therefore equal to 0. Now I write from the constraint that y is equal to 4 minus 1/2 x squared. That's not surprising. I look at condition number 2, which reads 3x minus lambda 1 plus lambda 2 is equal to 0. This, since lambda 2 is equal to 0 now, this is just 3x minus lambda 1 is equal to 0, and this means that lambda 1 is 3x. I'm going to use that later. I go into condition number 1, which reads 4x plus 3y minus lambda 1x equals 0. Now I plug in for y from here. So I get 4x plus 3 times 4 minus 1/2 x squared. You can see what I'm doing. Yeah, I'm repeatedly substituting so that I get one equation and one unknown. So here I'm shooting for one equation in x. Yeah, so lambda 1 I found to be 3x. So minus lambda 1 times x is minus 3x squared, be equal to 0. This certainly is one equation in x that I know how to solve. Yeah? Let me clean it up a bit. So I get 4x plus 12 minus 3/2 x squared minus 3x squared equals 0. So I get minus 9/2 x squared plus 4x plus 12 equal to 0. Now I multiply through with minus 2 over 9, so I get x squared minus 8 over 9x minus 8 over 3 equal to 0. Solving a quadratic equation, we get x1 and 2 equal to 4 over 9 plus or minus the square root of 1/4 times the coefficient of x squared, so 8 over 9 squared, that is 8 times 8, that's 64. 9 times 9, 81. And then minus the absolute term, so minus 8 over 3 is plus 8 over 3. And this is 4 over 9 plus minus the square root of 16 over 81 plus 8 over 3, which is 4 over 9 plus minus the square root of 16 plus 216 over 81. And this unfortunately is not a nice square root, so it remains as a square root 232 over square root of 81 certainly is 9, but I'm left with this term. So I have again two candidate values for x. I have to consider two subcases. Let's start with a positive one, 4/9 plus square root of 232 over 9. So I go into my expression for y, which was 4 minus 1/2 x squared, right? 4 minus 1/2 x squared. So this is 4 minus 1/2, and now 4 over 9 plus square root of 232 over 9 squared. So this is 4 minus 1/2 16 over 81 plus 8 times square root 232 over 81 plus 232 over 81. And after a few steps, you can convince yourself that this is equal to 200 minus 4 times the square root of 232 divided by 81, numerically roughly 1.717. This is less than 2. So since y is supposed to be bigger than 2, this is actually a violation of a constraint. And so this does not give me a candidate point, unfortunately, because I'm violating constraint number 2. So let's consider the second subcase, where x is equal to 4/9 minus the square root of 232 over 9. I can evaluate lambda as 3 times x, because this is essentially the fastest way to see that I'm running into a contradiction here as well. So this is 4/3 minus square root of 232 third, and this is a numerical value roughly equal to 15.2 something, so certainly bigger than 4/3. So this is a negative value, so I'm running into a contradiction here as well. I don't get any candidate points out of this case, despite all my gyrations to solve this equation for x. So I have to move on into case number 3, where constraint 1 is inactive and constraint 2 is active. This means that 1/2 x squared plus y is strictly less than 4, which means that the first Lagrange multiplier is equal to 0, and here activity means that y is equal to 2, and the Lagrange multiplier is therefore strictly positive. I go into Kuhn-Tucker condition 2, which says 3x minus lambda 1 plus lambda 2 equal to 0. Now lambda 1 is equal to 0, and therefore I get immediately that lambda 2 is equal to minus 3x. I go into condition 1, which reads that 4x plus 3y minus lambda 1x is equal to 0. Now lambda 1 is equal to 0, so I get that 4x plus y is equal to 2 because the constraint is active, so plus 6 is equal to 0, and thus I get that x is equal to minus 3/2, and then I get that lambda 2 minus 3 times x is equal to 9/2. This is positive, which is good news. So I get here a candidate point because by assumption lambda 1 is equal to 0, lambda 2 is 9/2, and x is equal to minus 3/2, y is equal to 2. So candidate point. xy is minus 3/2 and 2. Last case, both constraints are inactive. Slack, not binding. 1/2 x squared plus y strictly less than 4, and thus lambda 1 equal to 0. Y strictly larger than 2, and thus lambda 2 equal to 0. I go into condition 2, which now only reads 3x is equal to 0 because lambda 1 and lambda 2 are equal to 0. This means that x is equal to 0. Then I get from constraint 1, since now lambda 1, lambda 2, and x are equal to 0, this reads now just that 3 times y is equal to 0, and we get that y is equal to 0. So I get another candidate point where everything is equal to 0. And now I have gone through all 4 possible configurations of activity and inactivity of the constraints. I have exhausted the set of points that satisfy the Kuhn-Tucker conditions. I am left with 4 candidate points, and I can check the maximality of those 4 candidate points. So the objective function was 2x squared plus 3xy, and now we have the candidate points xy equal to 2 and 2. So I get 2 times 4 plus 3 times 4. This is equal to 20. Then I have the candidate point x and y equal to minus 2 and 2. This is 2 times 4 minus 3 times 4. This is equal to minus 4. Certainly not a better point. Then I have the candidate point minus 3/2 and 2. This is 2 times 9 over 4 minus 9. This is minus 9/2. Also not a winner. And then finally I have the origin, and there of course I just get 0. So clearly my candidate here is the point 2 and 2. So I can check sufficiency. Again, is the Lagrangian auxiliary function a concave function in the maximum, the optimum, well here, concave in the maximum, convex in the minimum. So again, plug in lambda 1 and lambda 2 from the optimal point. Those were lambda 1 equal to 7 and lambda 2 equal to 1. So the Lagrangian as a function of x and y is 2x squared plus 3xy minus 7 times 1/2, that's lambda 1, 1/2 x squared plus y minus 4, plus lambda 2 is 1, so we just get y minus 2. This, after cleaning up, is minus 3/2 x squared plus 3xy minus 6y minus 26. This is a concave function in x and y. Negative parabola in x and linear in y, and thus we have sufficiency. So indeed the case for point 2 and 2 strengthens. The only thing that's left to check is constraint qualification. Have we missed a point that does not satisfy constraint for qualification, but nevertheless is a maximal point? What are the gradients of the constraint functions? The gradient of the first constraint function is x and 1, and the gradient of the second constraint function is 0 and minus 1. When are they linearly dependent? Well, for x equal to 0. If x is equal to 0, we get from the first condition that 3y is equal to 0. This means that y is equal to 0. So the only point where constraint qualification breaks down is the origin, and that one we have already checked. It does not, it's the function value, the objective function value is 0 here, certainly less than our maximum value of 20, and so the points where constraint qualification breaks down do not give any higher function value, and so we have identified our maximum. Or maybe I should write this down before I close the case. So we have therefore established that the point xy 2 is the maximum of f given the constraints. And that concludes the second example, and this concludes the video. So thank you very much for watching.